Hello all, welcome back to Electronic Devices and Circuits video lecture series. I am BV Satyanarayana, Associate Professor in Department of ECE, Vishnu Institute of Technology, Bhimavaram. In unit number 3, rectifiers and filters, we already discussed about introduction, basic rectifier setup, off-wave rectifier, center tap to full wave rectifier, bridge rectifier, and off-wave rectifier characteristics. In this video, I am trying to derive the characteristics of center tapped full wave rectifier such as average DC load current IDC, average DC load voltage VDC, RMS value of load current IRMS. The objectives of this lecture are derivation for average DC load current IDC, derivation for average DC load voltage VDC, derivation for RMS value of load current IRMS. There are 12 characteristics for center tapped full wave rectifier. In this, the first characteristic is average DC load current IDC or I average. So this is the output of center tapped full wave rectifier. In this, the current is flowing through the load during both positive and negative off cycles. Here we are arranging our load in such a way that during the negative off cycle also the current flowing through the load is same as that of the positive off cycle current. So since the output of the center tapped full wave rectifier pulsating in nature, so we must calculate IDC. Consider one cycle of load current IL from 0 to 2 pi to obtain the average value, which is DC value of load current. So the load current IL equal to Im sin omega t for 0 less than omega t less than pi. But from pi to 2 pi, the current IL is again positive. But the sine waveform, it is negative. Hence, in the region pi to 2 pi, the positive IL can be represented as the negative of Im sin omega t. So, IL equal to minus Im sin omega t, that is pi less than or equal to omega t less than or equal to 2 pi. So during this period, our sinusoidal waveform is negative, but the output it is positive. So that positive IL current, we are representing it as a negative of Im sin omega t. Then IDC can be calculated by using integration over one complete cycle. So IDC equal to integral 0 to 2 pi IL d omega t, and total it is divided with the base, that is 1 by 2 pi. And very clear, we can write this expression as 1 by 2 pi integral 0 to pi IL d omega t plus 1 by 2 pi integral pi to 2 pi IL d omega t, and substitute IL. Then this equation it becomes 1 by 2 pi integral 0 to pi. So IL from 0 to pi is equal to Im sin omega t plus 1 by 2 pi integral pi to 2 pi. Now from pi to 2 pi our IL it becomes minus Im sin omega t d omega. Then IDC equal to, so in both the terms Im is common, so it is Im by 2 pi integral 0 to pi sin omega t d omega t minus integral pi to 2 pi sin omega t d omega t. Then integrate Im by 2 pi into integral sin omega t, it is minus cos omega t with limits 0 to pi minus of minus cos omega t with limits 0 to pi. Then applied the limits. Im by 2 pi into minus cos pi minus cos 0 is equal to minus of minus 1 plus 1. Then minus into minus it is plus 1 minus of minus 1. Then Im by 2 pi into 4. Then it is 2 times. So our IDC is equal to 2 Im by pi. So that is the final expression for IDC. These are the limits from pi to 2 pi. Sorry, pi to 2. Yeah. So in general, the output of full wave rectifier is the combination of two off wave rectifiers. Two off wave rectifiers conducts in alternative off cycles. Hence, for full wave rectifier, we can find the average DC load current as off wave rectifier IDC plus off wave rectifier IDC. IDC for one off wave, two off wave rectifier. So IDC for off wave rectifier is Im by pi plus Im by pi. So IDC equal to 2 Im by pi. So likewise also we can calculate. IDC equal to 2 Im by pi, that is the average DC load current. Okay. So means the average DC load current it is doubles for full wave rectifier. In off wave rectifier there is no load current during negative off cycle, whereas here in full wave rectifier there is a load current for even negative off cycle also. That's why IDC it is double that of the off wave rectifier. The second characteristic of center tapped full wave rectifier is average DC load voltage, and this is the equivalent circuit used to calculate the average DC load voltage. Here RS it represents the secondary winding resistance, RF is the diode forward resistance, and RL is the load resistance. The current that is flowing in this circuit, I am assuming it as a IM or IDC. Since we are concentrating on DC values, it may be IDC. So the average DC load voltage VDC, the average DC load voltage VDC is equal to IDC into RL. IDC we already calculated, that is 2IM by pi into RL. Then I am trying to calculate IM. So I am assuming the current flowing in this circuit is IM. So the secondary voltage is VM. Means VM must be equal to IM into RS plus IM into RF plus IM into RL. So VM equal to IM into RS plus RF plus RL. So from this, IM equal to VM by RS plus RF plus RL. Then substitute this IM in this expression. So we are getting VDC as VDC equal to 2 into VM by 2 into VM into RL by pi into RS plus RF plus RL, and manipulate this equation as VDC equal to 2VM by pi into RS plus RF by RL plus 1. Yeah, RS and RF are internal resistances. Those are very, very small compared to RL. So we can neglect RS plus RF by RL when comparing it to 1. Then the VDC becomes 2VM by pi. That is the final expression for VDC. As we neglected RS and RF, then only we are getting VDC equal to 2VM by pi. Okay, means we never used this equation directly. We are getting this one after neglecting RS and RF. Okay, so practically first calculate IM. From that IM, calculate IDC. Then from this IDC, we can calculate VDC as VDC equal to IDC into RL. Okay, this is the best way to calculate the VDC. So VDC equals 2VM by pi, that is the approximate equation. By neglecting RS and RF only, we are getting this equation. Then the third characteristic of center tapped full wave rectifier is RMS value of load current. So I already told the AC values magnitude can be calculated by using RMS. Since our center tapped full wave rectifier output consists of AC component, we can calculate the magnitude of the load current by using this RMS value. Root means square value. Okay. So I already told RMS value can be calculated by squaring, calculating mean, and applying the square root. So IRMS equal to, I wanted to calculate the RMS of load. So take IL, then first squaring, RMS first squaring, then calculate mean. Mean means average. Average can be calculated by integrating over one complete cycle. So 0 to 2 pi d omega t and whole divided with 2 pi, that is the average, and then apply square root so as to calculate the RMS value. So that is the equation to calculate IRMS. Then very clear, it is equal to 1 by 2 pi integral 0 to pi Im sin omega t whole square sin omega t whole square d omega t plus again 1 by 2 integral pi to 2 pi minus Im sin omega t whole square into d omega t. Then this Im square it is common, so you can take it out. So Im square by 2 pi integral 0 to pi sin square omega t d omega t plus integral pi to 2 pi sin square omega t d omega t. Then integrate. Then our IRMS is equal to square root of integral square root of Im square by 2 pi integral 0 to pi sin square omega t, it is 1 minus cos 2 omega t by 2 d omega t plus integral pi to 2 pi 1 minus cos 2 omega t by 2 d omega t. Then apply integration and substitute the limits. Then it becomes Im square by 2 pi into pi plus pi. So square root of Im square by 2 pi into so here we are getting a 2 1 by 2, then it becomes 4, so it is 4 into 2 pi. So this pi it's cancelled and it is 2. So our IRMS equal to Im by root 2. So that is the final expression for IRMS. This represents the magnitude of the AC component present in the output of offer rate. Coming to the summary, in this lecture we have learned the following: derivation for average DC load current IDC, derivation for average DC load voltage VDC, derivation for RMS value of load current IRMS. In the next lecture, I am trying to derive the expressions for ripple factor, thank you all.